Okay, so you know how light is made of photons, right?
The quantum particle of light.
And the other fundamental forces, like the strong and weak nuclear forces.
Yeah, the ones inside atoms and involved in radioactivity.
Exactly. They have their own messenger particles too, gluons, W and Z bosons. It's a neat picture.
It is a very elegant quantum description. Each force gets its carrier.
Which leads us straight into our deep dive question. What about gravity? Does it fit?
Ah, the big one. Well, if that pattern holds, gravity should have one too.
And scientists have a name for this theoretical particle.
They do. It's called the graviton, the proposed messenger for the gravitational force.
So the core question we're digging into is, does this graviton actually exist? Is it real? Or is it just, a concept?
Precisely. It's a concept that actually goes back quite a way to the 1930s.
Right, when physicists were first grappling with how to merge quantum mechanics.
Which demands particles for forces.
With Einstein's totally different view of gravity as, the bending of space-time itself.
Yeah. Exactly. A fundamental tension right there. It's a fascinating puzzle.
And what's really interesting, I think, is what quantum theory actually predicts about this hypothetical graviton.
Oh, yeah. It predicts it should be massless. For one,
Not the photon.
like the photon, yeah, travels at light speed. But it also predicts it should have a unique property called spin. A spin of 2.
Spin 2. Now, why is that specific number, spin 2, so important?
Well, that's the really neat part. A spin 2 particle mathematically aligns perfectly with the way gravity is described in general relativity as a tensor field. It means it interacts with space-time itself, warping it, not just acting on objects in space-time.
Wow. Okay, so that spin 2 property is like a theoretical bullseye. It matches Einstein's picture beautifully.
There's a very strong theoretical argument for it.
But theory is one thing. Finding it is another. You hear it's incredibly difficult to detect, like astronomically hard.
Oh, absolutely. Gravity is just unbelievably weak compared to the other forces.
Right. Like the classic example, a tiny fridge magnet lifting a paperclip.
Yeah, that little magnet is overcoming the entire gravitational pull of the Earth.
So if it's that weak, how could we possibly detect a single graviton? You'd need something enormous, right?
People have done the calculations. You'd probably need a detector roughly the size of Jupiter, parked near an intense gravitational source like a neutron star, just to have a chance. So direct detection is, well, let's just say it's off the table for now.
Okay, so no giant Jupiter detectors anytime soon. What about indirect evidence then? Does anything hint at gravitons?
Well, the biggest hint came in 2015, the detection of gravitational waves.
Ah, the ripples in space-time from colliding black holes. Huge news.
Huge news. And while those waves are macroscopic phenomena, big ripples.
Yeah, how do big ripples tell us about tiny quantum particles?
It's kind of like how sound waves are collective effects of many, many air molecules vibrating. You can think of gravitational waves as potentially being a coherent state, a collective effect of countless gravitons working together.
Okay, so it suggests an underlying quantum nature, like the wave is made of something.
It strongly suggests it, yes, but it's still indirect. We're hearing the sound of gravity, the wave, but we haven't isolated the individual molecule, the graviton particle itself.
Gotcha. So this leaves us kind of stuck in a debate within physics, doesn't it?
Absolutely. There are essentially two main camps.
Camp 1.
Camp 1 says, look, if gravity is truly a quantum force like the others, then gravitons must exist. It's just how quantum field theory works.
And some theories even need them, right? Like string theory.
Exactly. String theory is fascinating because it doesn't just allow for gravitons, it sort of predicts them automatically. In string theory, all particles are tiny vibrating strings. And one specific vibration mode of a closed loop of string has precisely the properties of a graviton massless, spin 2. It just pops out of the math naturally.
That's pretty compelling. A theory where the graviton isn't just added on, but is fundamental.
It is. But then there's Camp 2.
Okay, what's their take?
Camp 2 wonders. Maybe gravity isn't like the other forces. Maybe it doesn't need a particle. What if Einstein's smooth, continuous space-time picture is the fundamental reality? At least for gravity.
So, in that view, maybe quantum mechanics needs to be modified when it comes to gravity, not the other way around.
That's the idea. It's a genuine clash between our two most successful theories of the universe. We don't yet know which description is more fundamental when they meet.
So, for you listening, you might wonder, okay, theoretical physics debate, why should I care? What's the big deal?
Well, imagine for a second we did prove gravitons exist. If we found definitive evidence.
What would that mean?
Oh, it would be a revolution. Probably Nobel Prize territory. Easily. It would likely be the key missing piece to unify gravity with the other forces into one single framework.
The theory of everything physicists dream about.
That's the grand prize, yes. And beyond that, think about the practical implications, maybe far down the line. Understanding quantum gravity could unlock the deepest secrets of black holes, maybe the very beginning of the universe, the Big Bang.
And maybe even crazy-sounding technologies.
Who knows? People talk about manipulating gravity.
Yeah.
Things that sound like pure sci-fi now. Gravity-based propulsion, maybe? Controlling space-time.
Floating cities. Okay, maybe getting ahead of ourselves.
Uh-huh. Maybe a little. But look at history. Discovering the electron gave us electronics. Understanding the photon gave us lasers, fiber optics, the internet.
Right. Fundamental discoveries often lead to technologies you couldn't even imagine beforehand.
Exactly. Gravitons, if real, could represent a similar kind of leap for civilization, eventually.
So it's a truly tantalizing prospect.
It really is. So for now, the graviton remains this elusive thing. Is it out there? One of the universe's quietest whispers, just waiting for us to build sensitive enough ears?
Or is it perhaps just a beautiful idea, a kind of mirage our theories created in the quest to make everything fit together?
That's the mystery. And the search for gravity's quantum voice, however faint it might be, continues.
A really profound place to leave it. What an incredible scientific journey still unfolding. Something for all of you to think about.